Okay, let's look at a following question. We have an electric field of an electromagnetic wave in a medium. And so basically, before we go into the question, we need some background on electromagnetic waves. Electromagnetic waves are waves in electric and magnetic fields, okay? What we need to understand are certain rules that they follow. The first rule that they have to follow is that the electric field, the magnetic field, I'm going to represent that with blue. Magnetic field stands for B. The direction of the electric field, so I'll put it vectorially. The direction of the magnetic field, I'll put that also vectorially. And the direction of propagation of the wave, of the EM wave. So I'm just going to write EM wave for that. Okay, I'm going to put an arrow mark to show direction of them. All three must be mutually perpendicular to each other. They have to be perpendicular to each other. That's rule number one that electromagnetic waves have to follow. The second rule that they need to follow is that the electric field and the magnetic field must be in phase with each other. Must be in phase. And they should have the same wavelength, they should have the same frequency, everything is necessary, but along with that they must be in phase, meaning at any one time I find the electric field vector is at its maximum, I also should find magnetic field vector to be at its maximum, and so on and so forth. One more important concept we need to know is that the direction of the electromagnetic wave should be, so I'm going to say EM wave direction. We know it's perpendicular, right? We know it's perpendicular to electric field and magnetic field. But it should also follow this rule. It must be in a direction of E cross B. It should be in this direction, okay? So these rules must be followed, and one last rule is that the magnetic field must always be equal to the electric field divided by the speed of the wave. Speed of the wave. Okay? So these are necessary, but there's one more, I can't leave that out. There's one more thing we need to know. The speed of the wave. Should I tell you that? Okay, I might as well tell you. The speed of the wave, I told you the velocity of the wave only depends upon the properties of the medium, and that's no different for electromagnetic waves as well. It only depends on the property of the medium. What properties, you ask? Well, it depends upon two important numbers called as the mu naught and the epsilon naught, and it turns out to be 1 divided by mu into epsilon. Now if you have not seen this before, forget about it. We are not going to use this for a long time. I don't think so. Yeah, anyways, you're not going to use this for a long time. Don't worry about that. But if you have seen it before, then that's going to be what it is. I'm not going to explain what mu and epsilon are. It's not needed, but that's not really needed. I hope you get these four. Okay, please put this in your mind, and then we're going to solve the question on electromagnetic waves. Okay, cool. Let's do it. All right. So in our question, in our particular question, we have been given that E of x is 0. So let me just write that down. We know the x component of electric field is 0. We know that the z component of electric field is 0. And the only thing that's given to us is the y component. And that's given to be 2.5 cos 2 pi times 10 to the power 6t minus pi times 10 to the minus 2 x. Yeah, that's it. Okay, that's EY. Now, what else is given? We need to find the wavelength, speed, and frequency of the wave. Ha! That's easy. That doesn't matter whether it's electromagnetic wave or not. We just equate it to the standard form, so let's do that. Well, notice this is omega, and this is k. So we know what omega is. That's 2 pi 10 to the power 6. Okay, and that is 2 pi f, and 2 pi cancels, so we have the frequency. That's 10 to the power 6 hertz. That's 1,000,000 hertz. It's astounding, right? 1,000,000 oscillations per second. And what is oscillating, you ask? Electric fields and magnetic fields. They are the ones who are oscillating. Okay, we got the frequency. Next thing is we look at this and we'll get the wavelength. K is pi times 10 to the minus 2. That's 2 pi divided by lambda. And pi cancels, and from that we get the wavelength to be, this cancels, you get it to be 2 divided by 10 to the minus 2. And that is 200 meters. Whoa. That's a pretty big wavelength. 200 meters. Okay. Alright, now comes the velocity part of it. Now we can calculate velocity as f times lambda, or we can just do omega by k. I'll just do omega by k. Omega is given 2 pi 10 to the power 6, and k is given as pi times 10 to the power minus 2. This cancels. You get 2 in 10 to the power 8 meters per second. That's the velocity. Now, I'm pretty sure you have heard that the velocity of light is 3 in 10 to the power 8 meters per second. So how is it 2? Well, that's only in vacuum, so this is not vacuum. In fact, you know what else we can figure out? Well, it's not asked, but let me just do that. We can figure out what is called as the refractive index. We define the refractive index of a medium as the velocity of light in vacuum divided by the velocity of light in that medium. And in vacuum it's 3, in this medium it's 2, so the refractive index is 1.5. This is like a bonus. Again, if you have no clue what refractive index is, never mind. But this is like glass, okay? This is glass. Alright, so that's it. Okay, now let's go to part B. Okay, the part B asks me for the components of magnetic field. So I need to figure out what does the magnetic field look like. Let's see. The first and the foremost thing is I need to understand what direction the magnetic field is. So for that, remember I told you that electric field, magnetic field, and the direction of propagation must all be perpendicular to each other. So let's look at electric field. Electric field is along the y direction. So let me just draw the XYZ coordinates. I'm going to call this as X. Let's call this as Y, and let this be Z. Okay, so we know electric field is along the Y direction. That means electric field is oscillating this way. This is our electric field. Okay, fine. We also know from looking at this minus sign, there's a plus sign here and a minus sign here, that our wave is traveling in the positive X direction. So our electromagnetic wave is moving this way. So wave is traveling along positive X. Electric field, so let me just draw that. Here is electric field. This is E vector. It's along the Y direction. And here's the wave. And the wave is traveling along the X direction. Question is, what direction is magnetic field? Well, the only remaining direction now is Z. But there can be two directions, positive Z or negative Z. Well, that's where we're going to use the fact the direction of propagation must be E cross B. So let's ask ourselves, what direction should be B so that when I do E cross B, I get positive X as the answer? We can do that using our right hand rule, or we can using mathematically vectors. Anyways, I like the right hand rule. Look, I know cross product is given this way, right? This way. And we want the wave to be propagating along this way. And electric field is already in this direction, so B should be coming out of the page so that when I cross it like this, I get X direction. I hope that made sense. So B should be along the positive Z direction when electric field is along the positive Y direction. Okay? Alright, so if you find that hard, I have another method for you. Let's use unit vectors. We know the electric field vector is along the J direction, and we know that the wave is propagating. I'm just going to put C cap for propagation of wave. That's along the X direction, that's I cap. So we need to ask ourselves, what should I cross J cap with? So J cap So it has to be E cross B, right? So J cap cross what gives me I cap. Now if you know vectors, you know that it has to be either a plus k or a minus k. The way we're going to solve that is I'm going to put an I, J, K over here. And I know I cross J gives me K. And J cross K gives me I. And K cross J gives me minus I. All this is covered in vectors. So in order to get positive I should cross J with K. So that tells me that the B of Z, that is the Z component of the magnetic field must be, the magnetic field must be along the Z direction. From this, we understand that the X component of the magnetic field must be 0. I'm going to use blue to write the answer. Okay, so Bx must be 0. And By must also be 0. That's not allowed. The question is, what is Bz? What is Bz? Well, let's see. Bz is going to be some amplitude, which I don't know, but it should have the same form. Rest of the stuff must be exactly the same over here, because it has to be in phase, it has to have the same frequency, same wavelength, everything same, alright? So it has to be the same form, so it's going to be something times cos 2 pi 10 to the power 6 t minus pi 10 to the power minus 2 x. But what is that something? Well, to find that something out, we will use something we just learned a while ago. We learned that magnetic field must always be electric field divided by the speed. Must always be true. We know the speed and we know what the electric field vector is. We can calculate what the magnetic field vector is. So if we look at the amplitude, even the amplitudes should obey that particular rule. Therefore, the amplitude of the magnetic field must be the amplitude of the electric field, that's given as 2.5. So 2.5 divided by the speed of the wave, and the speed is over here. So 2 10 to the power 8. I'm running out of space over here, so I'm not going to simplify this. I'm pretty sure you can simplify this yourself. So there we have it. These are the components of the magnetic field of our electromagnetic wave. So I hope that wasn't too overwhelming, because electromagnetism is not officially covered in this course yet. But that's it.